I can just okay. The topic of my presentation is the analysis of instantaneous pointing vector for N-Layer Lossy Optical Waveguides and applications in evanescently coupled optical devices. The aim of this paper is that I will start with deriving the analytical expressions for the spatial evolution of instantaneous pointing vector in optical waveguides, and then I will take up the applications of instantaneous pointing vector in evanescently coupled optical devices with emphasis on surface plasmon resonance based sensors. I will start with the introduction to the optical to the pointing vector, giving a historical background of the pointing vector, and then I will derive the expressions for the analytical expressions for the spatial evolution of instantaneous pointing vector. Then I will show that I'll be proposing a new formula for the penetration depth of the instantaneous pointing vector, and I will show that this is different from the formula for the penetration depth of average pointing vector. And then I will take up the applications of this newly proposed formula for the penetration depth in case of evanescently coupled optical devices, and I will be taking two examples of surface plasmon resonance based sensors. I will start with the introduction of the pointing vector. Now, starting with what pointing vector is. A pointing vector deals with the flow of electromagnetic energy, and by definition it is given by S, vector S is equal to the cross multiplication vector product of E and H. Now, going to the historical perspective of pointing vector. The Poynting theorem was given by Poynting in 1884, and it deals with the conservation of energy for the electromagnetic field. This formula was first given by Poynting, and a very good reference to read about the basics of pointing vector is Feynman Lectures, Volume 2, Chapter 27, and he starts with the conservation of energy for electromagnetism. Then he explains what is a local conservation and what is a worldwide conservation. A worldwide energy conservation says that total energy of the universe is conserved, but it is seen that the electromagnetic energy conservation is a local process. So it is not just an energy density in a given region of space, but also a vector to represent the rate of flow of energy through a surface. For example, if there is a light source which is radiating, say for example at A, then the light energy is moving out from the source. So if there is some mathematical surface surrounding that light source, then the energy lost from inside the surface is equal to the energy that flows out from the surface, and which is equal to the energy that flows out of the surface. So while trying to write the quantitative expression for this conservation of energy through this equation of continuity, where you see energy density. So this is the energy flowing out per unit time, energy density flowing out per unit time, then this is equal to the rate of flow of energy per unit time across a unit area perpendicular to the surface, or given by the energy flux. This is the energy flux, and this is the while solving. So this particular continuity equation, Poynting derived an expression for this flow, and it is given by S is equal to E cross H. So it is actually basically a derivation, it is not a proof. So after this definition, there were lots of debates and alternative definitions. For example, Dielectric vector, Newton vector, and infinitely many vectors which satisfy the Poynting theorem of conservation of the electromagnetic energy. And E cross H being the simplest may be considered the best of all. Now coming to an optical dielectric waveguide. So generally when we try to study the time average pointing vector. The measuring instruments which are used to plot the intensity distribution, they are able to measure the time average effect because the optical frequency is very high. So we do not, actually look into the instantaneous behavior of the pointing vector. So in this presentation, I'll be doing some calculations to derive expressions for the instantaneous pointing vector. So for that, I'm considering a 3-layer optical waveguide consisting of, see, the center layer, I'm assuming that it is a metal which has a the complex value of the dielectric constant, and it is surrounded by N1. N1 is the core, which is the metal core, and N2 and N3 are the dielectrics. These are the dielectric regions. It is infinite in extent in y direction, and the transverse plane is the x plane, x direction, and the direction of propagation is taken as z. And d is the thickness of the core, which is metal in this case. So if so this is an absorbing structure, so because the refractive index of the core is a complex quantity, so the propagation constants, the longitudinal as well as transverse propagation constants, which are associated with this particular structure, with this particular waveguide, they are also complex in nature, and these are seen to be called the surface plasmon modes. And it is seen that such a structure supports only the TM modes and not the TE modes. So now again, I will revisit the aim of the paper. The aim is to derive analytical expressions for the spatial evolution of instantaneous pointing vector in optical waveguide, and then we will discuss the applications of instantaneous pointing vector in surface plasmon resonance based sensors. So that is why the waveguide which I'm considering in this particular presentation is a absorbing waveguide, which consists of metal and dielectric layers. Now, starting from the Maxwell's equations, which includes the Gauss's law, the isolated magnetic charges do not exist. This is the Faraday law, and this is the Ampere's circuital law. These are the equations in the differential form, and these are the corresponding equations in the integral form. Now, for a normal all dielectric waveguide, the TE mode equations have the non-vanishing components as Hx, Hz, and Ey, and the TM modes will have the non-vanishing components as Ex, Hy, and Ez. But in our case, since we are considering the surface plasmon modes, so we will be having only the TM modes. So I will be discussing just about the TM modes. So for the symmetric and anti-symmetric modes, the expression for Hy, which is the magnetic field, is given by, it has, for the symmetric case, it has cos dependence along the transverse plane, that is the x direction, and in the direction of propagation of the wave, see, Vr and Vi are the real and imaginary components of the longitudinal propagation constant. So I have bifurcated the two. So this is the attenuation. This basically says that such waves, they attenuate and they have a certain finite propagation length. This is the expression for the region which is inside the metal, and the lower equation is the expression for Hy as a function of x and z in the cladding region, which is the dielectric region. Now, these are the corresponding equations for Ex and Ez in the metal region and in the dielectric regions. Now, doing the calculations for the pointing vector states that S is equal to the vector product of E and H. So, for the TM surface plasmon modes, the non-vanishing components are the X and Z, and these are given by minus H by Ez and H by Ex respectively. Now, substituting the values of Ex, Ez, and Hy, these are the two expressions for the X component and the Z component of the pointing vector. See, this is the transverse component X, and this is the longitudinal component, which is in the Z direction. Inside the metal and in the cladding region, the dielectric region. Similarly, this is the inside metal and inside the surrounding dielectric region. So if we go for the average Poynting vector. I would like to point out that in case of average Poynting vector, the time average of the transverse component of the Poynting vector is 0, and only the z component, which is the longitudinal component, it contributes. Now, that means if I go back to the previous equation, this time average of this particular thing is 0, and if I look at the expression for Sz, it has a finite propagation length which is given by 1 by 2 beta I, right? And in the x direction, if I look into in the dielectric region, it has an exponential minus 2 gamma x expression, which signifies that the Poynting vector from the metal dielectric interface, it decays and it has a finite penetration depth inside the dielectric, and that penetration depth is given by 1 by 2 gamma from this particular component. That means the penetration depth of the average Poynting vector is given by 1 by 2 gamma, and the propagation length of the average Poynting vector is given by 1 by 2 beta I. Now, if I let me go back to these two equations. Now, in case we are interested in finding the Poynting vector flux lines for the instantaneous case, then we will now try to combine the Sx and Sz components in such a way that we get an expression for the Poynting vector flux lines as a function of x and z of the waveguide, and the expressions that we get for the TM symmetric mode, it is given by these two expressions. These symmetric modes are known as long range because their propagation length is greater than the antisymmetric mode. So C1 and C2 here are the complex constants whose absolute values give the strength of the Poynting vector, instantaneous Poynting vector, at any point x and z of the waveguide. So this is the expression inside the metal, and this is the expression in the cladding dielectric regions. The expressions for antisymmetric modes is like this. Again, C3 and C4 are the complex constants whose absolute values give the strength of the instantaneous Poynting vector at any position x and z. Now, if I look at this expression along the z direction, the dependency is cos of beta r square by beta. Since beta is a complex number, so this expression beta r square by beta will have a real part and as well as an imaginary part. The imaginary part of this number, this particular expression, will be responsible for the decay of the Poynting vector flux lines as it propagates along the z direction. Hence, the propagation distance, propagation length in case of the instantaneous Poynting vector will be given by the imaginary part of beta r square by beta. And if that is simplified, it is seen that the imaginary part of beta r by beta simplifies to give an expression 1 by beta I. We will discuss it later in the later slides. Now, looking at the dependence of x dependence, it says that it is beta r square into x by gamma in the cladding regions, in the dielectric cladding regions. I am interested in this. So, the penetration depth in case of the instantaneous Poynting vector is now given by the real part of gamma by beta r square. So that means the penetration depth of instantaneous Poynting vector is the real part of gamma by beta square, and the propagation length of the instantaneous Poynting vector is given by beta r square by beta, which simplifies to 1 by beta I. So this is basically twice the propagation length of the average Poynting vector. Now I will discuss the applications of this proposed formula. First of all, I will discuss the design methodology of a graphene-based SPR affinity biosensor with an addition of a thin layer of silica for detection of E. coli-like bacteria. Secondly, I will discuss the case when a thin silicon layer is introduced between the gold film and graphene in a conventional SPR sensor to enhance its sensitivity. And lastly, I will be showing you the penetration depths of various dielectric materials calculated using our proposed formula, and it is seen that this can be used as the optimum thickness of that particular dielectric material to be used as affinity layer or for enhancement of sensitivity in the SPR based sensors. Now in the first application, this is the diagram. This is the SPR sensor in the Frischmann configuration consisting of a prism gold layer, a single layer of graphite, which is graphene, then an affinity layer followed by the sensing medium, which is water in this case, which contains the biomolecule. And I would like to emphasize that this is actually an evanescently coupled device. A sensor is an evanescently coupled device, and the changes which are taking place in the biomolecule layer here within the penetration depth will be responsible for change of this angle theta I, at which the incident light is able to excite a surface plasmon mode at the metal interface. Now it is seen that if the affinity layer is chosen as silica, then depending upon the wavelength of incident light, it is seen. Here I have plotted the pointing vector instantaneous as well as the average pointing vector. The solid lines without stars correspond to the average pointing flux lines, flux, and the solid lines with stars is the instantaneous pointing flux. And it is seen that the instantaneous pointing flux, it drops very quickly. The penetration depth in case of silica, it varies between 22 to 27 nanometers depending on the wavelength which is used. And whereas for the average pointing vector, the penetration depth is very large. It goes as high as maybe 200 nanometers or so. Now, what we have done, we have chosen the thickness of the affinity layer, which is silica, to be equal to the penetration depth of silica, which is calculated using our proposed formula. This is the penetration depth of the instantaneous pointing vector in silica. So depending upon choosing this as the thickness of the affinity layer, this is the reflectivity curve versus the incident angle, which is generated using transfer matrix method. And it is seen that if the thickness is varied, thickness of the affinity layer, that is silica, is varied, then it is seen that for this particular value, the sensitivity comes out to be the maximum, which is supporting our argument that the penetration depth formula can be used to calculate the thickness of the affinity layer for optimizing the performance of the SPR sensor. Now, another application is a thin silicon layer is introduced on top of the gold layer in typical SPR sensor. And it is reported by many researchers, for example, Lahav and Gupta, that a thin layer of silicon as thin as 5 nanometers, maximum 5 nanometers, is able to enhance the sensitivity of this particular sensor quite a lot, but not more than that. And we have calculated the thickness, the penetration depth of the instantaneous pointing vector in silicon layer using our proposed formula, and it comes out to be equal to 4.56 nanometers, and which is a very close match to 5 nanometers. And this is again the reflectivity curve versus the incident angle. And it is seen that beyond 4.56 nanometers, the reflectivity curve starts to rise and the full width at half maximum. You can see that this broadens. And doing the sensitivity calculation, it is seen that the sensitivity actually enhances for this particular thickness of the silicon layer. Now here, we have calculated the optimum thickness of the dielectric, various dielectrics. These are the dielectrics with the reflective indices, and these are the corresponding SP supporting metals which are used in that particular SPR sensor. And these are actually the penetration depths of the instantaneous pointing vector in these dielectric materials. It is seen that the optimum thickness increases as the reflective index decreases. So, and it is seen that this thickness, when we are using the optimum thickness calculated using our proposed formula, it is very close. It is in a very close match with the formula proposed or reported by the researchers. Like this, the serial number 5, 6, 7, 8, and 9. These are the these results match with the experimentally reported results already published. So I will conclude that we have proposed a new formula for the penetration depth of the instantaneous pointing vector, and we emphasize that this formula can be used to find applications in the design methodology of evanescently coupled optical devices such as SPR sensors, EETM polarizers, and directional couplers. And we have discussed the design methodology of SPR sensors in detail in the present presentation. So these are the references which we referred for pointing vector as well as the sensors. Thank you so much.